Hello, good morning. Today we will go through the infinite impulse response filter, that is IIR filter. In this particular case, when the impulse is applied as an input to the filter, the response extends up to the infinite time period. That is the meaning of IIR filter. The digital signal processing published by Wiley India publication is published by me. I am the author of this particular book. For further details, you can go through this particular book. So we'll first consider what are the basic design concepts for IR filter. Now in case of IR filter, the analog filter design is well established and we use this analog filter design and we simply map the analog filter in the digital domain, that is from S domain to Z domain. The digital filter design starts with the analog design and then mapping of the analog filter from Laplace domain to the Z domain, that is the digital domain. These IR filter designs, they are based on different mapping functions, and depending upon the mapping functions, they will have different names. Now, requirements of a mapping function. Now, how the mapping function should be? There has to be a direct one-to-one relationship between the S domain and the Z domain. It can be one-to-one in the ideal situation, or it can be many-to-one. A stable analog filter after mapping must result in the stable digital filter. Otherwise, it is of no use if the digital design becomes unstable. And the second thing is, whatever is the impulse response of the filter in analog domain, it should be same as the impulse response of the filter in digital domain. So we'll mainly concentrate on method of mapping of differentials, which comes with backward difference method and the forward difference method. Then we have impulse invariant technique, and then we have bilinear transformation method. So we'll go through these methods one by one. Mapping of differentials. Under this, we have backward difference method. We also have forward difference method. Now, what happens in case of the backward difference? We map the backward difference, that is yn minus yn minus 1, that is the difference of the current sample with the previous one, backward sample, divided by t, and this difference is mapped onto d dt of yt at t is equal to n into t. So, if we take the S transform of left hand side and Z transform on the right hand side, we take transforms. So, left hand side becomes S into Ys. It will transform into 1 minus Z inverse Yz upon T. So, S is equal to 1 minus Z inverse upon T is the equation for mapping. So, in other words, I can write it as Z is equal to 1 upon 1 minus St. This becomes the mapping function for backward difference method. Now, see how the mapping is. Let us map the frequencies. So we'll have to put S is equal to j omega, and then we'll put Z is equal to x plus iy. So we'll put Z is equal to 1 upon 1 minus j omega t, because it is 1 upon 1 minus S into t. Now we will rationalize this. So we'll have 1 upon 1 plus omega square t square plus j omega t into 1 plus omega square t square. This is after rationalization. Now we put z is equal to x plus jy. So x minus half the whole square plus y square, what it will be? It is equal to 1 upon 1 plus omega square t square, that is means x minus half the whole square plus y square. What is y? Y is this omega t upon 1 plus omega square t square. So z, I am writing it as x plus jy. So this is x and this is y. So let me substitute x in this equation. So x is 1 upon omega square t square minus half raised to 2 plus jy. So what is jy? This is j, and this is y. So y square will be omega square t square upon 1 plus omega square t square raised to 2. Now, when I simplify this, I get it as equal to 1 upon 4, 1 by 4. So x minus half square plus y square transforms to 1 upon 4. So it maps onto a small circle in the domain with radius equal to half and center at half 0. So this is how it is. This is the circle with center at half 0 and the radius is equal to half. So this is a circle in Z domain which we get after mapping the entire S domain. Right. So when S is equal to 0, the equation is Z is equal to 1 upon 1 minus ST. Now when S is equal to 0, Z will be equal to 1. So S is equal to 0, I'll get Z is equal to 1. That is this point. Now when S is equal to J infinity, S is equal to J infinity, I will have 1 upon 1 minus J infinity. So I divide throughout by infinity. So 1 upon infinity divided by 1 upon infinity minus 1. So it tends to minus 1. So this point maps on to Z is equal to uh, Z is equal to 0. See how this is. I am putting S is equal to omega t and S is equal to J infinity. So this is J infinity. 1 upon 1 minus J infinity. So 1 upon J infinity divided by 1 upon J infinity minus 1 it will be. So 1 upon J infinity tends to 0, 0 upon 1 minus 1 minus 0. So it will map on to 0, Z is equal to 0. When S is equal to minus J infinity, again it will map on to Z is equal to 0. So this point S is equal to maps on to Z is equal to 1. S is equal to J infinity and minus infinity map on to Z is equal to 0. What about this axis from J omega axis from 0 to J infinity? From 0 to J infinity, as we traverse in the Z domain, we traverse from Z is equal to 1 to Z is equal to 0 on this circle with radius equal to half and center at half 0. Similarly, when I am traversing from 0 to minus J infinity in S domain, I am traversing from Z is equal to 0, I am moving on to Z is equal to 0. So what happens is this entire j omega axis maps onto the circle in the domain with radius equal to half and center at half 0. What about the points on the left hand side of imaginary axis? All these points will map onto the inside or area of the circle, and the points on the right hand side of imaginary axis will map onto the area which is outside this circle with radius equal to half. So definitely a stable filter will give rise to a stable filter in Z domain when we map from S domain to Z domain. But the drawback is that the corresponding frequency response is not the same as the frequency response in the Z domain, because this entire j omega axis maps onto this small circle. It is not mapping onto the entire unit half circle in the Z domain, that is a unit circle in the Z domain. It is mapping onto this small circle. And what happens is that the corresponding filter response will change even though the filter remains a stable filter. So a stable analog filter will result in a stable digital filter because all poles on the left hand side of imaginary axis will map onto the area inside the unit circle in the domain, but it will be inside a inside a small circle. However, the locations of the poles of a digital filter are confined to a small frequencies, relatively small frequencies, and can be used for low pass filter and band pass filters only. The frequency response of the digital filter will not be same as that of the analog filter. Now consider the forward difference method. In this case, we will map this dy by dt or d dt of yt at t equal to nt to y of n plus 1 minus yn. So we are considering the forward difference divided by t. So in a way, I have the equation s is equal to z minus 1 upon t. Now let us see how the mapping is. Now in this case, the mapping is like this. This is S domain, this is the Z domain, this is the unit circle in Z domain. Now let us see what happens when S is equal to 0. When S is equal to 0, I put it in this equation, so I get Z is equal to 1. So this point maps onto 1. And when I am moving from 0 to j omega on x-axis, this becomes j infinity, 0 to j infinity rather, z becomes j infinity plus 1. So it is 1 plus j infinity. It is mapping onto this line. Similarly, 0 to minus j infinity will map onto 0 to minus j infinity. So it is not mapping inside the unit circle. So the corresponding filter will never be stable. So in this case, it is not recommended to use this forward difference method, because the stable analog filter will not map onto the stable digital filter. Right. So stable analog filter may not result in a stable digital filter. Frequency response to the filter is not same as analog filter. So this is of no use. You can say it is never used. Then we have impulse invariant technique. In this particular technique, the basic theme of this is we are considering that the impulse response of the analog filter will be same as or will remain same as the impulse response in the digital filter. So we take the impulse response as invariant. The design starts with the analog impulse response, that is HN, and what we do is analog impulse response will be first found out, and then it will be directly mapped on to the digital domain. That is, impulse response will be mapped on to H of NT. So H of S will be mapped to H of NT, that is S domain to Z domain. We know that the sampling of the analog impulse response will result in periodic function in the frequency domain. So what we are doing is we are taking the impulse response in the S domain and we are just sampling it. So we are putting S is equal to NT. Right. So when we sample the impulse response in time domain, in the frequency domain, it will result in the periodic spectrum or replicated spectrum. This replicated spectrum will this periodic spectrum in frequency domain will overlap if the sampling frequency is not below the Nyquist state. This already we know, and it will not overlap if the sampling frequency is above Nyquist state. So it will all depend on the sampling frequency. If the sampling frequency is appropriate, then definitely we can say that the aliasing effect will be minimal. So the design steps would be like this. Given the transfer function in S domain, we first find out the impulse response as h of t. Then we sample this h of t to get h of nt. So we put t is equal to nt, n into capital T. And then simply drop that t because t is constant and we get hn. And then we convert it into the z domain by taking z transform. So this is the procedure. Now, what is arising effect? Why it is arising? Because digital filter can have the same frequency response as the analog filter if the sampling frequency is sufficiently large to avoid the aliasing. But if you consider band pass filter or high pass filter, then the sampling frequency you cannot select as sufficiently higher as compared to the infinite frequency. So it is the impossible case, and in that case, aliasing becomes inevitable. So this is a periodic replicated spectrum, and in that case, there will always be some overlap if the sampling frequency is not sufficiently high. If I take this Fs at this point, then the periodic spectrum will not overlap. So this is possible in case of a low pass filter. So let us see the procedure for converting analog filter to digital domain. So let us consider we have the transfer function in S domain 1 upon S plus 1, S plus 2. So here there are poles at S is equal to minus 1 and S is equal to minus 2. So what we do now, we just decompose this transfer function in S domain using the partial fraction expansion. So we can write it as K1 upon S plus 1 plus K2 upon S plus 2. Then we evaluate K1 and K2. What will be K1? We will have to multiply by S plus 1 and evaluate it at S equal to minus 1. So we get it equal to 1. And what is K2? We'll have to multiply it by S plus 2 and evaluate it at S equal to minus 2. So when S is equal to minus 2, then this becomes equal to minus 1. So after putting the values of K1 and K2, I get HS equal to 1 upon S plus 1 minus 1 upon S plus 2. So now take the inverse transform. So I get Hn is equal to, Hn is equal to e raised to minus t minus e raised to minus 2t, isn't it? Now we'll put t is equal to nt. So e raised to minus nt minus e raised to minus 2nt. Now take the transform. So h of z will be z upon z minus e raised to minus t minus z upon z minus e raised to minus 2t. So it all depends on capital T, that is the sampling time interval or corresponding sampling frequency. So if the corresponding sampling frequency is low, capital T will be sufficiently large and e raised to minus t will be tending to 0. So in that case, it will be corresponding Z transform will converge. So the conclusions are the pole locations and hence the resonant frequency of the filter will change with the sampling frequency. It depends on Fs. We are not mapping the zeros of the S domain function, but we are mapping only the poles to the Z domain. So we cannot design high pass filter in this case using impulse invariant method because of the large aliasing effects. For high pass filter, aliasing will be unavoidable because you will have to have the corresponding sampling frequency very high. So aliasing for low pass filter is there, but it is relatively small, so we can use it. So let us consider the mapping from S domain to Z domain. This is the S domain and this is the Z domain that we have plotted. This is the unit circle in Z domain. Now Z is equal to e raised to S of t. This is the mapping. Now if I separate out the real part and imaginary part, Z I can write it as real part of Z into e raised to j omega. E raised to st, S is equal to sigma plus j omega. So e raised to sigma t, e raised to j omega t. Now put s is equal to 0 in this case. When s is equal to 0, what will happen? E raised to 0t, so z is equal to 1. So s is equal to 0 will map onto z is equal to 1. Is that okay? Z is equal to 1. Now, when s is equal to pi by t, when s is equal to j pi by t, okay, j pi by t, so that t will cancel and it will be e raised to j pi. Sigma is of course 0, so e raised to j pi, so e raised to j pi is equal to the mod value is equal to 1. So here it maps onto z is equal to 1. Similarly, when s is equal to minus j omega j pi by t, j pi by t, pi by t. So t will cancel, e raised to minus j pi. So it will transform to z is equal to minus 1. So when I am traversing from 0 to pi by t, I am traversing in the z domain from 1 to minus 1. Similarly, when I am traversing from 0 to minus pi by t, I am traversing from 0 to minus z is equal to 1 to z is equal to minus 1 in this case, because in this case the angle is minus pi. Now, if you consider the strip on the left-hand side of this imaginary axis between pi minus pi by t to plus pi by t, this entire strip will be mapping onto the z circle, unit z circle inside area. And if it is outside area in the z domain, outside means on the right-hand side of imaginary axis in S domain, it will map onto the area which is outside the unit circle. So if you consider this entire strip between minus pi by t to plus pi by t, this entire strip maps onto the entire z domain. And what about the strip between pi by t to 3 pi by t, 3 pi by t to 5 pi by t, similarly minus pi by t to minus 3 pi by t, all these strips will map onto the z domain again and again. So there will be, you can say, all these strips map onto the same z domain, and there will be what you can say aliasing all the time because all these strips are mapping onto it's on mapping onto themselves. This is also called as the fold back effect. These strips are folding back onto, as if the strips are folding back onto themselves. So stable analog filter will result in the stable digital filter, because if the filter is stable, all poles are on the left hand side of imaginary axis, it will map onto the area which is inside the unit circle. So the filter will be stable. But there will always be aliasing, though small, for smaller fs. The strip between minus pi by t to plus pi by t will map to the entire z domain. The strips between minus 2k minus 1 pi by t to pi into 2k minus 1 by t will again map onto the entire z domain. The strips in the s domain fold back onto themselves. This is what is called as the fold back effect. And because of this fold back effect, there will always be aliasing. So impulse invariant method is good for low pass filters, but it should not be used for high pass filters and band pass filters because it will result in high amount of aliasing. Then we have the best method called as bilinear transformation method. In this case, it is called, why it is called as bilinear transformation? Because S is written as Z minus 1 upon Z plus 1. So there is a linear transformation in the numerator, linear transformation in the denominator. That is why it is called as bilinear transformation. Or Z, if you write, Z can be written as 1 plus S upon 1 minus S. Again, it is bilinear equation. Now, how the mapping is, let us see. When S is equal to 0, what will happen? When S is equal to 0, what will happen to Z? S is equal to 0, Z is equal to 1. So, S is equal to 0 maps onto Z is equal to 1. When S is equal to J infinity, when S is equal to J infinity, 1 plus J infinity upon 1 minus J infinity, divide by throughout by infinity. So, I'll have 1 upon infinity plus 0 divided by 1 upon the infinity minus 0, so it will map onto minus 1. So this point maps onto minus 1. Similarly, minus j omega also maps onto z is equal to minus 1. And this area between 0 to j omega maps onto the unit circle in the z domain, half the circle, z is equal to 1 to z is equal to minus 1. And this area on the in the imaginary axis maps on again to z is equal to 1 to z is equal to minus 1, this half circle. So this entire j omega axis maps onto the entire z domain. If the area is on the left hand side of imaginary axis, it will map onto the area inside the unit circle. And if the area is on the right hand side of imaginary axis, it will map onto the area which is outside the unit circle. So this is, you can say it is one-to-one mapping. So there is no aliasing at all. If the filter in the analog domain is stable, it will result in the stable digital filter. So it will have the same frequency response. So there is, because there is no aliasing at all. And then we can consider this as the ideal mapping function, that is bilinear transformation method. But there is one drawback, and that is called as frequency warping. So if you consider the mapping, j omega a, that is S, is it mapping onto z minus 1 upon z plus 1. What is z? Z is equal to e raised to j omega d t minus 1. Omega d is the digital cutoff frequency, and omega is the analog cutoff frequency. So this e raised to j omega dt, I will write it as e raised to j omega dt by 2 into e raised to j omega dt by 2. This minus 1 also I will write it on the similar manner, and this is 1, so I will write it as e raised to j omega plus into e raised to minus j omega. So this will cancel and I'll get 1. So in place of 1, again I'll write in the same manner. In this case, e raised to j omega dt by 2 comes as a common factor, so it will be cancelled out. And in the numerator, you will have e raised to j omega dt by 2 minus e raised to minus j omega dt by 2 divided by e raised to j omega dt by 2 plus e raised to minus j omega dt by 2. But e raised to j omega dt by 2 minus e raised to minus j omega dt by 2 is nothing but 2j sine omega dt by 2. And this with plus sign, I'll have twice cos omega dt by 2. So it becomes j sin omega dt by 2. J will cancel on both sides. So omega a maps onto tan omega dt by 2. Now, if I just map it, try to map it, I will see that frequencies, analog frequencies between 0 to 1 will map onto 0 to omega s by 4. And the frequencies between 1 to infinity will map onto omega s by 4 to omega s by 2. So, the frequencies, large area between 1 to infinity, they are mapping onto a small area, omega s by 4 to omega s by 2. It is called as frequency warping effect. And this frequency warping effect is there in BLT method, otherwise it has no drawbacks. Now let us see how to convert the filter to the digital filter with considering fs is equal to 60 hertz and cutoff frequency of 20 hertz. So this is the filter given to you. the corresponding HS, the S domain transfer function, can be written as 1 upon S plus 1. This you are familiar with. Now what I will do is I will first do the pre-mapping. That means convert this omega d to omega a. So omega d is what? Omega d is 2 pi into 20 hertz. So it becomes 40 pi. And now omega dt by 2 will become 40 pi upon 2 into 60, because capital T is 1 upon omega s. So it is 60. That becomes pi by 3. So omega a becomes tan of pi by 3. So omega a becomes root of 3. Now we'll have to do frequency scaling. So what the corresponding transfer function is 1 upon s plus 1. Now this s will be replaced by s upon root 3, because this is the omega a that we are getting, corresponding omega a. So s upon omega a, if I substitute, I'll get omega root 3 upon s plus root 3. Now I will put s is equal to z minus 1 upon z plus 1, because this is the mapping that we are familiar with. We have seen that this is the mapping. So if I just simplify it, I'll get 0.634 into 1 plus z inverse upon 1 plus 0.268 z inverse. So I get the corresponding numerator coefficients and denominator coefficients for the filter, and that is how the filter is designed. The filter design means design a filter means design the numerator and denominator coefficients of the transfer function.